research engineer here at Antithesis. I'm also kind of a JavaScript guy, and I've worked a lot on our JavaScript-based user interface, and in particular on building out the testing infrastructure and bringing this thing under test. And today I want to talk about what we did and what we were thinking about and with building out this testing infrastructure and sort of how it went and what we learned from it. So to start off, what exactly is this Antithesis thing? We are an autonomous software testing company. So software has bugs, and we use some techniques to find bugs in. Press the button. Now it's on?
Yeah. Beautiful.
Okay. Software has bugs. We find bugs in other people's software. In order to do this, we write software, but software has bugs. One of the pieces of software we write is called the Antithesis Notebook, and it's our user interface. It's what we use to configure and set up and launch runs of our autonomous agent and our deterministic simulation environment. It's what we use to analyze the data that comes back from that environment, and it's how we render reports that show to our customers, to people who are testing their software with our system, what happened when we put their software into our environment. From a software engineering perspective, the Antithesis Notebook is a functional reactive programming environment, sort of like a cross between Jupyter and Microsoft Excel. Like Jupyter, it has cells that contain and execute code. In our case, we're running JavaScript inside the browser. Like Excel, it has some data flow analysis and dependency graphs under the hood so that when you change a value, all of the cells downstream of it that read that value recalculate automatically. And we have, mutable state containers and some other things. So just so that you can see what the system under test actually is, and I need to make this bigger. So here's an example of a notebook. We define this object A with the key foo and the value 3, and then we print it in a separate cell. And you can see these lines on the left that tell you where the cell boundaries are. When I change this to 4, the print cell recalculates automatically. But if I change this back to 3 and then I just edit this cell without changing the values that are coming out of it, this print call doesn't recalculate. And the way we do this is that we have this function equality hash, which for any value that can exist in the notebook, we produce a string representing the contents of that value. So if two values have the same equality hash, they're the same value, and we don't need to recalculate. And you can see this down here. I have this other object B with key foo and value 3, and these two objects are not equal by JavaScript's equality operator. They have different locations in memory, but their equality hashes are the same. And now if I change this to 4 so the values are different, the equality hashes are now different. So that's the system under test. And I'm not going to talk about it in great detail. I just want you to see the thing that we're testing here. And if we think about the list of components of our system, you can see these along the row and column titles here. And don't worry too much about what these things are. They're just parts of our system. If we think about the interactions between the components of our system, some of them are going to be a little trivial. We have equality hash, which, as you just saw, takes any object and returns a string. So if you equality hash an equality hash, you're just equality hashing a string, and it should be able to deal with that. Repr is our printer, and like equality hash, it takes any value and does something sensible with it. In repr's case, it prints it. If you repr an equality hash, you're just reppering a string. So this interaction, we hope, is pretty trivial. And it's not going to be a source of great complexity. And on this chart, I've colored those cells in gray. Most of the cells are not gray. Most of the possible interactions between these parts of our system, which are not only underlying pieces of notebook architecture, but are also made available to the notebook itself, have highly non-trivial interactions, and each of those interactions is a place where you can have bugs. And if you think about it from the perspective of someone who's writing a new piece of this system or working on maintaining an existing part of that system, when you're thinking about this one thing, you also have to think about every other thing and how it could interact with every other thing and all of the invariants that every other thing is trying to maintain. And this is just intractable. It's exponential. So while some bugs are atomic, and these are all real fixes from our commit message history, some bugs are atomic. You just have an off by one somewhere, or some facts about JavaScript are, for example, if you slice a validly encoded string, you may not get a validly encoded string back. And arrays in JavaScript can be sparse. So you can have an array with elements at indices 0, 1, 2, and 4, but nothing whatsoever at index 3, not even undefined. And this is distinguishable. These are behaviorally distinguishable. So if you're something like equality hash, which is making very strong claims about the behavior of an object, you need to care about this. But other bugs are combinatorial. They involve two parts of our system, multiple parts of our system interacting in ways such that one of them violates an invariant that the other one wants to maintain. For example, we have state var, which is a mutable state container. And it's a value or error type. So it has a get method where if you call get on a state var that contains a value, it'll return that value. And if you call get on a state var that contains an error, it'll throw that error. Repr is our, as I said, general purpose printer. And one of the invariants it wants to maintain is that no matter what kind of crazy object you give it, it could be an array that contains itself 100,000 times, it has to do something sensible with it, and it has to never throw. So repr's way of calling state var, calling get, is a problem because it means repr can throw. But when you think about it, JavaScript is a part of our system. Users of the notebook are writing JavaScript, and developers of our system are writing JavaScript. So JavaScript itself is another part of the testing complexity for this piece of software. We have crazy Unicode stuff that you have to think about, but it's another source of complexity. We have strange facts about JavaScript's array type. So we decided to use property-based testing for ensuring the robustness of this piece of software. And the components of notebook property-based testing, we wrote our own library and everything, are generators, which are strategies for transforming typed inputs into a typed output. So you could request, let's say, a number. One of the generators for number could take two numbers and add them together. One of the generators for number could take no inputs and always return, let's say, 3. And a generator for number could request a string and return the length of that string. We have combinators, which are functions from input type to input type. So a several of number would give you an array of numbers, and the system itself will decide how many elements that array will have. And we have defer, which will give you a defer of number, for example, would give you a function from no arguments to a number. And this is really nice if you want to, for example, defer some complex computation if you're not sure you're going to need it, or if you want to produce the same object twice, but have them be technically different because you're testing something like equality hash. And we have properties. So we just have a function called test assert, which takes a Boolean and a description. And if the Boolean is false, it'll throw an error with the description as the message. And when you think about what it means to use this system to produce a value, we have this sort of generator tree. So here you have your input type, and this input type has multiple generators associated with it, multiple strategies for producing values of that type. And each generator takes some number of inputs. So on the left, you have a generator that takes 2 inputs, and those inputs are both typed, and those types both have generators associated with them, and so on. And the one in the middle takes 1 input, and the one on the right takes no inputs. And when you go to instantiate that type, when you go to request a value of that type, the system will pick a generator and then say, okay, this generator has some inputs. I need to produce values for those types. And so on until you get to the leaf nodes, which are these little tiny things up here, or the one on the right here, which take no inputs. Now, another really cool thing we can do with this is, because we're producing this tree, and because we know what all we're doing to build this tree, and because these generators are written in TypeScript, which compiles to JavaScript, and because we have an interactive functional reactive programming environment for writing JavaScript, we can take these generators and stitch them together and produce a repro. And here's an example of the repro on screen. Don't worry if you don't understand this code. It's all computer generated. But this is code to produce a value that our PBT system generated. And maybe it ran some property checks. You see multi-step property check at the top there. So this is code to literally test a property of our notebook. So when we find a bug, the time between our system detecting a bug and engineers having a fully interactive reproduction of the bug that they can load into a notebook and play around with is like 2 seconds. You hit a button, you open a new notebook, you paste it in. And this is kind of a hard thing, a hard property to maintain, because our build system really wants to rename things, and because in TypeScript we're importing stuff from files, but in the browser we're just using a bundler and exporting these values to the notebook environment, maybe in some namespace. So it's kind of tricky to maintain. How do we maintain it? We have a test for it. We have a property check test for it, and it's called repro works. So this is an example of both a generator, because property check is just a type, but it's also an example of a property check, a test that we're using to assert some property of the notebook and tell us if it's not true. So what it does is it takes a generator from the type top level type, and something I haven't talked about yet is that types are hierarchical. So we have, for example, the type uint8, which gives you an integer between 0 and 255. We also have the type number, and uint8 we've defined as a subtype of number. So everything is in this type subtype relation all the way down to top level type. So we take any generator from our entire library of generators, we produce its value and repro, and we evaluate the repro as if in an empty notebook with the same library we're using and with a notebook fuzzer. Because if this thing is trying to talk to the outside world, the presence of the notebook fuzzer is what tells it to run our mocks instead. So we have a value, and we have another value that we've built by executing the repro that we got, and we just assert that they're equal. Another thing we can do with this is what we call the path independence test, which is how we assert the functional property of the notebook. So in one cell, we generate a new value and we mutate it over time. We build up a lot of history in that cell and give any state that might creep in plenty of opportunities to get in there. And then in a separate cell, every once in a while, we'll take the same thing we're doing in our first cell and generate it again from a different starting point. Those two things should be equal. And if they're not, then cells are maintaining hidden state that they shouldn't, and that's a bug. And something about this is it kind of has implications for how we want to mutate these values over time. We don't want to constantly blow them out and replace them with something completely different. If you think about it, that kind of weakens the test properties a little, because it'll tell you, okay, nothing goes wrong if on every tick you're getting something completely different, but what if you have the same thing for 10 ticks? Or what if you change one tiny part of the subtree? So we've taken some care to write our RNG so that each subtree is kind of independent of everything else and can be mutated without affecting the rest of the subtree. So here are the rest of the tree. So here we're generating a value for this type, and you see we go to the generator on the left, and it has two inputs, and they both go to the thing on the left, and so on. On the next tick, we could mutate specifically this part of the subtree, this pentagon on the left here, and it goes from requesting the one on the left to the one in the middle, but everything else remains constant, even the things that are evaluated after it. Now you might ask, how does this work in production? And the answer is it's really powerful, because we're harnessing that combinatorial power that I mentioned earlier with the graph of, here are our gray cells and here are our red cells. We're harnessing that same combinatorial power for good. So by adding one feature, you add n places to create new bugs. By adding one new generator, you add n new places to detect bugs. So when we added generators for sparse arrays, we added one generator. We wrote that in one place, and we found all of the bugs that involve sparse arrays. The spread operator in JavaScript is a little unsafe. If you call it with, so what the spread operator does is it takes an array and it spreads it into, here are all the arguments to this function. And this is unsafe because if you have a really large array, you can blow out the call stack. So when we tuned our array generators to generate really long arrays, we flushed out all the bugs with, here are all the places where we're using the spread operator and shouldn't be. When we added a generator to produce -0, this is just one generator that produces a number, and it found 5 bugs. Are you really going to remember -0 in 5 different places in 5 unit tests? And there are sort of 2 different modes that we can use this in. On the one hand, you're writing new code and you're trying to bring that new code under test and make it as robust as possible. And on the other hand, you're not actively involved in writing new code at the moment. You're not writing new features. You're just thinking about how do we make our existing tests more powerful? And I'll talk about those in order. So first of all, when you're writing new code and you're bringing it under PBT, you really benefit from having a centralized repository of weirdness. If you're writing a function that wants to take a double, and until very recently, JavaScript's only numeric type was double, you don't have to remember every single detail of IEEE floating point to write good tests. You just say, this function takes a number, and the PBT library does it for you. And the PBT library already knows about -0 and nan and infinity and the smallest positive integer for which n+1 is equal to n. But there are some questions. How do I know how comprehensive my tests are? How do I know how comprehensive my generators are? And in the kind of simplest case, if you have a function that takes a number or a string, you want to test it when it's taking a number and you want to test it when it's taking a string. But if you have a function like equality hash that takes a totally arbitrary value, thinking about, am I testing this function with all of its input types is maybe a little harder. But you have these pre-existing generators, and if you don't, you can define them easily and in a centralized location to produce things like typed arrays and blobs and all the other weird JavaScript objects that can exist. We can use sometimes assertions to get visibility into what our code is doing. A sometimes assertion is just a line of code with a description and a function call that's like, whenever I see this line of code, I'm going to increment a counter associated with this description. And when our tests finish running, we read out all of those sometimes assertions and how many times we hit them, and if too many of them are 0, or if too many of them are like 1 or 2 instead of 10,000, we can tune that. We can use code coverage, which is not really the end-all and be-all of test coverage, but it is very nice to be able to, let's say you're writing a new class and the class has a bunch of methods and you bring it under test and you run your tests and it's like, half of the public methods of this class were not hit at all. Okay, probably add more tests. And most importantly, whenever we find a bug that we did not find with this property-based testing, maybe something happened in prod, maybe one of our engineers was playing around with the notebook and happened to notice something funny. Before we even go and fix the bug, unless there's some horrible production emergency, before we even go fix the bug, we update our tests so that our tests can reproduce the bug. And there are some questions about, how do I use PBT for this? Because a lot of examples of PBT that you see on blogs and so on are talking about getting building block functions under really robust tests. So you have your encoders and decoders, you have your format parsers, but we're using it also to assert really high-level properties about parts of the notebook and even the notebook itself. So how do I use PBT for this? For complex APIs, you have the base case and mutators pattern, which Alp talked about. You start with a simple case and you build up from functions that transform one of these objects into one of these objects. You build up, maybe you take your base case and you add another key or whatever, but you don't just do this you don't need to only do this for complex APIs. You can also do it to generate numbers. You start with a number and a function from number to number. You apply that function to that number. It's the same principle to build up these really complex objects, although it can be kind of tricky. For stateful operations, we have the rollout pattern, which I got into a little bit in the context of the path independence test. So it's the same principle. You take some block of time and you say, this is going to be my rollout. So my rollout is going to last for 12 ticks, let's say. On the first tick, you initialize your stateful object, you initialize your global, you can only have one of these per notebook or whatever. Or for a stream, you pre-calculate, here's all the stuff that over the course of the rollout, we're going to push into the stream. And over the course of the rollout, you run your operations against your thing. And sometimes you have validations that you can run in line. So while you're adding new content to the stream, while you're running new actions against the session, and the session, by the way, is just how the notebook communicates with our autonomous agent and with our deterministic simulation environment. But you're running these actions over the course of the rollout, and then at the end of the rollout, you run your end validations, the things that you can't do in line but that you really want to test, and then you tear the whole thing down and get ready for the next rollout where you're going to initialize a new thing from scratch. And this really forces you to know where all your state is so that you can clean it up at the end. If you don't clean it up at the end, you'll probably have a state bug somewhere. And you can leverage existing assertions. So a property is expressible in the form of an assertion. And you can write assertions in your property checks. You saw the property check earlier, but you can also write assertions just in your code. So as the system is feeding weird values to your code, it's exercising all of the assertions that exist in your functions. The other mode of using this and of thinking about this and improving this is how do we improve test power in general? So we have this combinatoric thing, and I'm really coming back to this. More features means more squared bugs, because every one of these things is going to interact with potentially every other thing in your system. But more generators means more squared test power, because if you add another generator, that generator is already being used by your existing tests. So you're just adding power to all of your tests. And we also think a lot about distributions. So we have this time to bug graph here, where the experience of using this is, let's say you're writing a new feature, you run the tests against it, and it finds all the bugs in your generators really quickly. So that's over here. You fix those, you run it again, it finds some silly off by 1 or something, that's over here. And you're running this for a very short amount of time. It doesn't take that long to find these and flush out these initial bugs. And you fix those, and then you run it a little longer, and you chop off the whole head of this distribution over the course of running it and getting it through a review and onto the main branch. But there's still this tail of bugs where you would have to explore for a really long time to find these bugs. And then over here, there's the stuff that your tests aren't powerful enough yet to find. What you want to do then is pull things out of this unfound category into anywhere in this distribution, even if they're way out on the tail, and pull things from the tail of the graph toward the head. And an example of this is we had a bug in sequence, which is a type that we've designed to mirror the JavaScript array API. So all the methods on array should also exist for sequence. And this has to do with some stream handling stuff. I won't get into it here. But one of the methods on array, thus one of the methods on sequence, is at, which works like array index access in Python. If you give it a non-negative integer, it'll return the element at that array, at that index. If you give it a negative integer, it'll count from the end. So -1 gives you the last element, -2 gives you the second to last element, and so on until you get to negative length, which should give you the first element. We had a bug where sequence.at negative length returned undefined instead of the first element. And it took us 2 weeks of automated testing to find this. This change was made on a branch. We ran PBT on the branch. The branch was put up for a review. We ran PBT on the branch in review. The branch landed, and we ran nightly PBT for 2 weeks before we found this bug. So, okay, what happened there? And if you think about that generator tree from earlier, what was happening under the hood is that we produce this sequence, and that sequence has some length. The sequence generator says, I'm going to produce a sequence of length reasonable number. And that's at one part of the subtree. On a completely different part of the subtree, completely different part of the tree, once we have this sequence, we need to decide which number we're going to call at with. And those two numbers had to be, you have n here and you have -n there. It's really unlikely, with the way our distribution of numbers was at the time, it was just really unlikely to get n here and -n here. But we want to be able to reproduce this bug quickly. So what we did was we just added generators to reasonable number that return one that returns -2, one that returns -1, one that returns 1, and one that returns 2. And this tiny change got us down from maybe 16 hours of testing time to bug to 5 minutes. So it really pays off to think about input distribution in this context. But how do you know how good the input distribution is? How do you know how good you are at finding these sort of unknown unknowns? So on the one hand, something that research fuzzers like AFL know is that some numbers are more interesting than others. Some values are more interesting than others. If you have a function that takes a uint 8 and there's a bug in that function, it's more likely that that bug happens when you give that function 0, 1, or 255 than only happening if you give that function like 37. But sometimes it does happen only when you give that function 37, and we actually had an example of this. We have a hot path UTF-16 to UTF-8 encoder, and there was a bug in it, and the way to find that bug was to guess the one uint 16 that would trip the off by 1 and falsify the property. And we found it with PBT. We can use sometimes assertions and generator call counters to every generator has a sometimes assertion embedded in it. So when our tests end, we get a readout of here's how many times we hit each of these generators. And if that number is 0, okay, we probably want to tune that. If that number is 10 instead of 1,000, we probably want to tune that as well. But adding more generators, and this is kind of counterintuitive, can actually weaken the test. Let's say you're testing a function like equality hash that can take a totally arbitrary value. So you have some any value whatsoever generator. And you add 2 to the 32 generators to that any value type, one to produce every uint 32. Your tests are going to be a lot weaker. They're still, in principle, capable of finding a bug where you have to pass it, an array that contains itself or a string of length 10,000, but it's just much less likely, and it really helps to find bugs as quickly as possible. And we can use statistics and observability. All right, where'd it go? There we are. We can use statistics and observability, and here I have a notebook that generates strings and graphs the length of the string. So we can see in real time the distribution of the string length. And x and y, x is the length of the string and y is the number of times we've hit it, and both are log scale. But so whenever we generate a string, and here you can also see the gradual mutation that I talked about earlier in the context of the path independence test, because the active bubble is not just flashing around all the time. We have sort of the same thing, or sometimes we make a little mutation to it, but we do want to have a good distribution over change rate as well. So in short, for using PBT in production, the two main takeaways that at least I got from doing this were the combinatorial power. Your tests should have the same combinatorial power as your actual system. If adding a new feature can produce n bugs, if adding n features can produce n squared bugs, maybe even worse than n squared. You could have a bug that only happens when 3 components work together in exactly the wrong way. But with this property-based method, with this generator-based method, one improvement increases the power of all of your tests. So it's sort of the same thing, but harnessing that power for good. And for distributions, once you have your tests, once you have your properties in place, once you've expressed the invariance that all of your functions should maintain, you can improve all of your tests further by pulling bugs toward the head of this graph. Here's the real PBT, the powerful barbarian Tamandua. That's all I got. Any questions? Yeah. All right.
Really great talk. I just wanted to ask if you guys have looked at using coverage-guided techniques at all, or if you're all sort of working off pure random generation.
These notebook tests use pure random generation. We can sort of tune the distributions, but it's not coverage-guided. This developed alongside the notebook itself, so the techniques we had available were a little limited.
Thanks. Great talk.
So do you do any type of caching at all, or like, let's say that you generated some values overnight? Do you reuse some of those values, or do you regenerate it every like whenever you're running the test from scratch?
We generate new values every night,
Okay.
but we try to generate a lot of values.
Yeah, like because like this has been a long going discussion. Like, does it make sense to cache values, or like just put them in a file and read them all the time, or like do you have any experience with that? Did you think about that?
I know there are some fuzzers that have this test corpus-based approach, but for this test, we're not doing anything like
Okay,
that.
thank you.
Back there again. And then over there.
Sorry, I have a lot of questions. Have you guys considered mutation testing at all? This is one of the things we've been looking at for judging how good your test coverage is, and I'm just curious if you guys have looked at it.
Can you define mutation testing?
Oh, sure. So the idea is you want to inject artificial bugs into your code and then run your testers to make sure that your testers find your injected bugs.
Yes.
With the hope that those injected bugs are in some way correlating with real bug finding power.
Yes, this is definitely something that we do. You know, when we write generators, we want to, all right, let's just break something in our code and make sure our tests can catch it.
Extremely cool.
Yeah, somewhat similar question, but you know, you're writing the libraries or you're writing all these generators. That itself is code. So how do you write a generator for generators? So you can test your generator code to make sure you're generating the right code to test the right code to be generated.
That's very meta.
All right, please give another round of applause.